Hello. Hello. Okay, good afternoon. I think you all can hear me. Okay, good afternoon. Uh let me start today's lecture. So this week we will talk about the backtracking. So we only on the remaining lecture, we will talk about a few things. One is the backtracking to solve some problem. So we will introduce some, I would say it's very classic computer science problem, which you may find there are some similar problem in real world, which also can apply the solution. So that's why all this problem, although it's already more than 100 years problem, but we still discuss it. And as a computer science or computer engineering student, you should, yeah, you need to know all these problem, because when people discuss, yeah, they were surprised as a computer science student never heard about the coloring problem. They don't know what is n-queen problem or n-queen problem, and so on and so forth. All these are very typical classic computer science problem you need to know. Yeah, so I will briefly talk about a few of them. Of course, there are a lot more. Like earlier, I have mentioned Tower of Hanoi. Tower of Hanoi also another quite well known. Later in the next level, in 2101, I think they will introduce more, and especially they will emphasize about their time complexity. That's why you may heard about like MP hard problem, MP problem, P problem, all this. Yeah, these problems are related to it. And we only introduce is about like actually they can use the backtracking algorithm to solve it. But doesn't mean that backtracking is give you the best solution. In the end of this lecture, I will let you know that actually they are not the best solution, or this problem right now there's no so-called the best solution. Yeah, people have not think out any best solution, because a lot of time you will find that all this problem you need to try out. You have to try out all the permutation combination, then you can find out the solution. If you don't do that, you are just try, you can improve, but no matter how you improve, you still need to try all the permutation. So you can reduce the number of permutation, you can remove certain number of permutation, but in the end your time complexity is still in exponential or in factorial level. Is very hard to further improve. Yeah, that is this kind of the characteristic of this kind of a problem. And but real world we really have encountered this sort of a problem, and we need to take notes that the solution may take you a lot of time to complete. Yeah, so the time complexity, the order of growth is very high. Yeah, it can be normally is in exponential or can be n factorial. Okay, so we will talk about this week, and then probably this Wednesday, if time allow, or next week, I will talk about some, I think, quite well known problem, or always come out in the some job interview, which is the dynamic programming. We will briefly introduce it. More will discuss in the, maybe also will discuss, especially the time complexity will be discussed in the next level as well. And then the last topic will be covered in week 11 or 12, depend my progress. Like, yeah, the last topic is about the matching problem. Matching problem, I think I have mentioned in the very first lecture, that is one of the very classic, is like job assignment, or some or the matching. Like for example, you in the future you take your final year project, you select the project, and then everyone also select the project, but in the end we need to find the best match to get to assign everyone one assignment and one project, and there's no two students assigned to the same project, and every we try to let every project be assigned to one of the students. Yeah, then that is a very classic matching problem. In our daily life, we encounter a lot of this kind of similar problem. So we will introduce that the algorithm to solve this. You will find that somehow, yeah, breadth first search or depth first search can be applied in part of the solution. So roughly this is the coming 3 weeks we will discuss about. So today we just talk about the backtracking. I think last Wednesday we have talked about the breadth first search and depth first search. And this week tutorial we will discuss one of the question is the breadth first search. And then I think the next week, this week have a tutorial. Next week there is no tutorial. The last tutorial will be conducted in week 12 or week 13. There's some group because due to week 12 Friday is Good Friday, so we have to postpone the tutorial to week 13. Yeah, then that one will talk about this coming week's content and depth first search. That will be the last tutorial. Then lab wise this week we have the lab. I think this week is about the graph representation and then breadth first search, and next week will be the depth first search and some backtracking problem. We will try it out. I also will release the assignment soon. Yeah. So back to this last week, what we have covered about the depth first search is you can see that maybe need to recall what is the first search. Okay, here. Okay. So depth first search, depth first search is if you have a graph, maybe something like this. Maybe. Okay. So you let's say I start from here. Change the color. If I want to use the depth first search algorithm to search every node once, visit every node once, and then if you use the depth first search algorithm, means that it's a kind of a greedy strategy. Whenever you maybe I start from here, as long as I will use a stack or whatever. This is the algorithm, but the idea we trying to understand the idea is that we are trying to travel as far as we can. So once I found that there's one adjacent node which is unvisited, I will quickly go and visit it first. I don't care there's another one at this moment. I will move on from these nodes. I will look for another nodes. As long as there's an adjacent node which is unvisited, I will trying to travel as far as I can until I reach the point which there's no any unvisited nodes. Then I will backtrack. So backtrack is like when you reach certain point, there's no more path or nodes or unvisited nodes are available around. Then the option you can have is you need to backtrack to the earlier nodes and look for alternate path to look for the alternate path. That is why that when there's no unvisited vertex adjacent to the W, you will pop up. This process corresponding to the graph. The effect is like you trying to backtrack to the earlier nodes and look for, and then carry on from that nodes and look for any unvisited nodes around. Any unvisited nodes is adjacent to it, then you will carry on another path. Yeah, so you will try this path and then backtrack, yeah, and so on and so forth. So that is the idea behind of a depth first search. And in our daily, why this idea is very useful, because in our daily life, yeah, suppose you have a series of decision and you have a lot of choice. So, but you every time you don't know what is the, of course you don't know the solution. If you know the solution, you don't need to try all these possible cases. So you don't normally when you visit the nodes, just like something you will find that the problem you will be like you visit the you travel in the graph. When you visit the nodes, you only know that the adjacent nodes. You only know, you don't have the full information at that moment. You only know that the adjacent nodes information only. So whether it's visited or unvisited, yeah, whether you can reach there or not. So then you may choose one of the possible solution, but that may not be the correct one. It's possible is the correct solution. It's possible, and you may have more than one possible solution to the problem. Then you choose one of them, you try. If it's not working, you will try another one. You can try, and you need to try another one until you found the solution. So that is how the backtracking works. And yeah, that is the idea of the backtracking. And you can find what are the problem. For example, you can see that something like this, like what I just now I mentioned to you. Yeah, starting you don't know whether this is the solution, but there's a path, this is one possible combination, or this is a possible path you can try. Maybe it's a solution. When you go to another node, after you make this decision, you move to another nodes to make the decision further. Then your solution is a series of decision. It's a series of decision. Or you can imagine it's a path for you to move. Then this is one of the possible path. But it may not be the solution. Because when you keep moving to certain point, it's no more. And this is not the solution you want. Then you will backtrack. You will try another possible path. Then you may trying to, okay, this one is still not the one. You will backtrack. Then you will try another one. Maybe still can move further. This is not the one. This is not the one. When is the result? Okay, this is still not the one. Okay, yes. Then this is the one you want. Let's say you reach certain point you found. Then you have some function or something to evaluate whether this path is correct or whether you already achieved what your objective. Then you confirm that this particular path or this particular decision is the result, the solution you want. Then you found the solution. And okay, then at this point, usually we will stop because we already found a solution. But also doesn't mean that in this whole graph, in this problem, this is the only solution. That means if I carry on the journey, I may find more solution. So that is possible. So as I mentioned in last week, yes, is sort of a post-order traversal. Just like binary tree, all this is, you find that actually is you can consider those binary tree is a special case of graph problem, which means that those tree have no cycle inside, of course. Then yeah, you are just using the depth search algorithm to visit all the nodes in the tree. Yeah, you find that tree post-order traversal, those post-order traversal, pre-order, in-order, they are using a stack. In the earlier slide, this anime. In the earlier slide, I also show you that depth search also use a stack. And also the strategy we are using is kind of a greedy strategy. We just travel. When you are in the mid of, when you face a problem, when you are in the mid, at this point you have no idea that maybe when I am here, I need to make a decision. Actually, there are two choices. Later you can, in just now the result, you can see that in this particular point, I have two choices. Actually, at here, I got two paths. But at this moment, I don't know which one. Actually, when I'm here, I have no idea the correct path is this one. I wouldn't be able to, like I said, if I know, of course, you look at the result, you know that answer is there. But when you have a very big graph, and where every time you only visit one node, you have no idea which path is give you the best solution or is the solution. That path is the solution. Then you only can try all of them. Then Then the strategy you can choose is like you are here, you want to move, you need to make a decision to move to the next node. Yeah, which one is better? No idea. Just choose one of them. Greedy strategy. I know there's one. This one can move. Then I try this one. Only when I reach certain point, I know that the solution is not this one. Somehow it's not this one. This is not the solution. Then I will backtrack. I will try another path. If this is not the one, I will backtrack. I try another one. And then this one no more option for me. I backtrack. And then I try this. I found that this one still have another solution. Then I also try. Sometimes you look very silly to try all this wrong solution, but no choice. At that moment, the information I have only can tell me that this one maybe, this one also, both are possible. Then you only can try all the possible case until you found the solution. And that's one thing. Another thing I need to highlight is like this when you found a solution, it's just a solution. It may, in the whole graph, they can have more than one solution, which satisfies the criteria you want. Yeah, for example, that one of the application probably you can think of is like solving a maze. Yeah, solving a maze, you want to find a path. You just want to find a path to from the source, from the entry to the exit. That's it. I don't bother the path is shorter or longer. I just need a path to get out from this maze. Then you can choose to use this backtracking strategy, which means that of course there's a limitation for the maze that in this particular example you can move straight, you can turn left, can turn right. Of course you can move back lah. Then, and let's say the maze is very huge that you won't be able, you use your naked eyes to find out the solution. You are in the maze. Imagine you are in the maze, you are inside. You are somewhere inside. You are somewhere here. Yeah. Then you only can move for your capability. You only can make a decision is like you want to move straight, move left, move right. Yeah, that is the option you can have. Then no other choice. You just try your luck that just like at this moment I can move forward, I can turn right. I only can have two valid. Of course I cannot turn left because there's a wall here. Then in that case I only have two choice. Which one is the best? No. Then you have to try. Maybe you are unlucky, you choose turn right, then you move in this path. Then you found that this is not the correct one. Then what can you do? You only can backtrack to the earliest step and then try another path. Let's say the worst is that you are always very unlucky. Then you will try this one and then backtrack. And then you try this one, you will backtrack. Then you try this one, you try until you can be here, then backtrack. That is the worst scenario. Yeah. Of course, doesn't mean you have to visit all the nodes, all the possible path. Then you get it out. Then you solve the problem. So you can see that this particular problem actually can be solved by backtracking. Every time you move, you get some idea. Yeah, this is the solution or this is not the solution. When you cannot move further and you haven't reached the destination, that means this path is not valid, it's not correct. Only at that point you know that the answer is this is not the correct path. Then you need to find the alternate one. So you will find that this kind of a maze problem can be solved by the backtracking algorithm. What I would like to highlight you again is like this example you can see only one path. But sometimes the maze can have more than one path. Will it be end out? No. Because once you visit the place, you won't revisit again. That's what the depth search trying to do. If you end in the loop, that means that you keep repeatedly visit the same places. So there's no once the place is visited, you already make a marker that this particular path is not possible. So you won't go back. You already visit this path. You won't retry again. So you will choose those those possible path which you have not tried, which you have not been visit earlier. Then you keep doing this. Eventually, if there's a solution, worst is I also can be there's no path for you to get out from this maze. So there's a possible is that you keep try. Then when you cannot find any path further, and you backtrack to the starting point, means that you still cannot find out a path to get out from, to reach the destination, to reach this location. That means that this maze is no solution. It's possible also. So that means that before you use the backtracking algorithm to visit the possible path, it can be only one solution, it can be more than one solution, it can be no solution. But after you try it, the result can tell you there's one solution or multiple solution or no solution. But before you try, you don't know. You need to know that you don't know. So this is one of the typical backtracking algorithm can solve a maze problem. Another one is quite well-known problem is coloring a map. Then you have this is, I think, is United States. You want to color each state with different color, and all the adjacent not more than n color. Very classic problem is 4 color is good enough. There's a proof. This one is beyond this scope. I'm not talking about the 4 color problem. I just want to color. It can be any number. Just I do not reach. I need to ensure that when I choose the color, I need to ensure that adjacent region must be in different color. That means if this, I don't know, this state is choose red color, then this one and this one cannot repeatedly choose the red color. I only can choose yellow, purple, or green. So that's what it means. So of course at the beginning you haven't started the color, you don't know whether it can be done or not. Then you just try. The color. Very intuitive is I just try, choose one color, then all the adjacent region, I just choose different color. I keep trying. If when I reach certain point I find that it cannot work, then I have to uncolor a region. The last one I color, I just uncolor it and then try another alternate color. I keep trying this. Not surprising, backtracking happen. So each choice will lead you to another set of a choice. Every time you color one region, then the following uncolored region, you have a set of options. Maybe for this example, I think I have 1, 2, 3, 4. Maybe you have one choice, maybe you have 4 choice. But you don't know which one is the correct answer. You only can try. So there are many possible sequence. So you only can try each of them. If this particular sequence is not working, you don't have to carry on. You don't have, obviously you won't carry on. Once you reach certain point, you don't have to force yourself to finish the coloring. When you reach certain point, you already found that this particular sequence is not working. Then you have to choose the alternate one. Then you will stop there and carry on to find another alternate sequence. So that is another backtracking algorithm. You can think that it's like you form like a tree. Imagine there's a tree. You start from the first region. You start with the first region, then you try another color. Every time you will keep trying different sequence. And different color. So when you are coloring, you can carry on your color. That means that you can move on. But when you are color the second state, you color the third state, you don't know that whether this is the correct solution. You keep doing this. When you reach certain point, you reach so-called a leaf nodes. You can say it's a leaf nodes, or you reach certain point, you find that there's no any option for you to color but there's no choice for you to color further. That means that is not the solution. You have to backtrack. Yeah, you have to backtrack until you reach the goal. So-called the goal in this particular problem is I be able to color all the state. Let's say US got 50 state, then you successfully visit all the nodes, all the 50 state, and color each of them, and ensure that all the adjacent region do not repeat the same color. Then if that is true, then that is the answer, that is the goal. Yeah, so that is what the thing's trying to do. So in short, to implement that, you can see that you are trying to expose each node. Each node represent a region, and then your algorithm probably will look like something like this. If you reach the goal, imagine that if you found the path, okay, that is the answer, then you will return success. If you reach a so-called leaf nodes, but this leaf nodes is not the answer, that means you cannot travel further, and you haven't finished the coloring the whole map. That means you only visit less than 50 state. You already cannot move on. Then you don't need to carry on. This path is not the answer. You can return failure and return back to the early stage and carry on. Then every time you are trying to, after you finish one color, you will just look for those uncolored region, adjacent region, and try to choose one of them and color it and carry on and carry on and carry on. So it's like you're trying to and repeat this procedure and repeat this procedure. Yeah, if the return value set success, then you already reached the goal. Yeah, and then you start return. Once you return success, that's when you carry on. You don't need to color further. You already finished. Then you will keep return success. So this part is a recursive. That means I'm trying to expose the end. That means this is every time you run a for loop, is trying to recursively call the function to test another alternate location. And that's the goal. Yeah, the goal nodes you can think is the leaf nodes. You can think that is when you reach that point, you won't carry on further. There's no more. Also, same thing. You reach that point, you will find that there's no more unvisited adjacent region or unvisited nodes available, because you already visit all the nodes in this particular example, in this particular problem. Yeah, it is the leaf nodes which is your goal. Then if it's not successful, if you go through all the possible case, or you cannot, that means that that means no solution. Like what I said, when you reach the leaf nodes, then you can't find any things, or you already try out all the possible path, then don't have solution, then you can return failure. There's no solution for this, maybe for this particular path. So you need to backtrack to the earlier nodes to let it find the alternate path. Yeah, so this is roughly the pseudo algorithm. So back to earlier that problem, that means that you can see that this one you need to use a recursive function. And if you look back to here, this one why this problem is hard, or this problem is not very good. Should I say not very good? You can expect that if you attend the last week tutorial, I have shown you that there's one algorithm which we have two recursive call in a function. When you have two recursive call in a function, and the time complexity of that algorithm is end up in 2 power to n. Yeah, so you expect that this kind of a backtracking algorithm, you run a for loop and and in this for loop there's a recursive function inside. So a lot of time you will end up the time complexity of this algorithm can be very scary. Yeah. That's in the possible, so you basically try out all the possible. You also can see that doing this way is you are try out all the possible cases. Yeah, if this path cannot, you try another path. If this path cannot, you try another path. If this path cannot, you try another path. It's like you try all the possible path available in a graph. And that the number can be very scary. Yeah. So you expect you likely use a recursive function. Yeah. Just like what I showed you earlier. That there's a you keep recursive, your recursive function is here. If success, so that means the worst case is that you keep you need to run a for loop and then recursive call in one call. In one function call, you need to do, if you have n you have how many, you have n child nodes, or you have n neighbor adjacent nodes, you need to try all of them recursively. This one cannot, then you try the next one. This one cannot, you try the next one. This one cannot, you try the next one. So the next nodes also repeat this recursively. The same process, you will do it recursively, repeatedly, and you need to try out all the possible paths. So it's very computational and expensive. Yeah. So the coloring problem, of course, like I mentioned earlier, initially you choose one color. You select, if you have a region, you just select one color. Then you'll find that nearby there's another 2 region or 3 region or X number of region. You just select one of them. And then color another color. And then if, of course, you will check whether this is valid or not valid. The third step is you check this is valid, yeah, because one green color, one red color. Then yeah, it's a valid color assignment. Then you move on. You repeat the step 2 and step 3. Let's set the next one. If I choose red color, of course, if I choose the next one as a red color is invalid, I will go to step 5. Then of course this one cannot choose the red color. I have to uncolor it. So I need to uncolor it. Then I need to try another color. No, this one no. Let me choose another color. Let's say I choose yellow color. Then I choose a yellow color. So maybe color this region. So if it's a valid, I can repeat the step 2 and 3. If not, then I will uncolor. It may be you need to uncolor more than one time. Backtracking once, no more solution, no more possible solution. You have to further backtracking to the earlier stage. Then to try alternate color. So until you manage to fill out the whole map, all the region is color, then that is the solution. But that also doesn't mean it's the only solution. I have to highlight this, is like it may be they're not surprising if all this color, yeah, you can reshuffle the index. If then at least they are easy, you can find out there are at least 4 solutions. More than that, I think more than 4. If I'm talking about 4 color, maybe all these color I can reshuffle the order. Then it will become another solution. So you can have more than one solution in this coloring problem. Sometimes some problem only have one solution. Sometimes have more than one solution. Yeah. Also depend on your implementation. If your objective is you just want to find one solution, as long as you found the solution, you stop. Or you try to find all the solution. If you want to try to find all the solution, once you find one solution, you still have to carry on. You still have to carry on those unvisited nodes to find more solution. So then that will be, yeah, then that's the way to find out all the solution. Depend the problem you have. Yeah. For this one, I think I just need to color the region. Maybe I just find one solution is good enough. Then I will just try. For example, in this particular 4 nodes, 2 color problem, you can expect that I have 2 possible. A can be choose green or blue color. There are 2 possible already. So of course, at the beginning, I don't know which is the solution. I choose one of the path. Maybe I try this one. I color the red I color the A as a green color. After that, after I color it, then I will move on the B or D. So I choose to color the B first. B, of course, I have two possible. I can choose green or blue because I can two color problem. I can choose green or blue. Then if I choose green, then this is not the solution because cannot invalid. As I earlier showed you that the algorithm, this is the invalid path. So this is not the solution. You have to backtrack. You have to uncolor the B, then you try another one. Not surprised. You only have another choice, which is blue color in this problem. Then after you successfully color the B, then you move on to C. C, same thing. You can choose. At this point, of course, you can choose green or blue. Then you try to color it. Then you check. Then of course you cannot color blue color on C because there's an adjacent nodes B is already colored in blue. Then you only can choose green. Then after that you try green or blue. Green cannot on D, then you must choose D. Then when you reach this point, yeah, like just now someone asked, yeah, is a leaf nodes, but you found that you already color A, B, C, D. You only have 4 nodes. You know that this graph only have 4 nodes. All 4 nodes is successfully color a unique color, either green or blue, and there's no any adjacent region. Any 2 nodes are adjacent region are not adjacent nodes are not color in the same color. Yeah, this is the answer. This is one of the solution. Because you look at here also there's another one. Not surprising. Yeah, you can be blue. I mean, if like I mentioned just now, if I reshuffle the green and blue in different order, then I can find another path. So that is backtracking to solve the coloring problem. So you expect implementation wise, you need, of course, you need to construct this particular map into a graph. That means I try to, let's say I just briefly draw out. Maybe here, this is 1, 2, 3, 4. So I just trying to build the graph, is trying to build this one with the purple color adjacent. Then there's this one, I don't know what is the state, sorry about that. Then this one adjacent to the red color and the purple color. Then this is, can't remember, Utah, is it? Or Colorado. Then this one is adjacent to it. Then the green color, this one I think is California or San Francisco, is it? Then this one adjacent to this one. Then this one should be this one should be this. Okay. Yeah. So this is the graph. So I trying to construct the graph, but of course I don't in the real implementation. I just need to know the adjacency, their relationship. So I just need the adjacency matrix or adjacency list to construct this particular. Then I'm trying to reformulate the problem into a graph problem. Then of course I need to decide the number of color. 4 color, 5 color, 6 color, up to you. Then the output is the answer, the color sequence. For each, for example, I can label each state is 1, 2, 3, 4, 5, 6 to 50. So each state, then you need to tell me the corresponding color in this color array. So state 0 maybe is Washington. State 2 is, I don't know, Boston or whatever, you name it. Then it's 2 or 3. Then I already label it. So you just need to tell me what color I should fill in. So it's like you need to implement this input output. Then as I said, that I think someone also asking, yeah, if you need to try all the possible scenario, the most naive is try out all the possible scenario. Then you will find that the number of possible cases, number of color power to all can be like red, green, red, green, yellow, red, green, blue, got blue, purple, yeah, yellow, yeah, all these combination. So it's n power to the number of vertex you have. So if you have 4 color, 64 vertex is 4 power to 64. Is something power 10 power to 38 if I remember correctly. That is a lot. The computation time is very expensive. You use backtracking, you can reduce a little bit, because when you try to travel certain path, you find that it's not like red, don't need to try. You try cool red color, you already know that it's not valid already. You don't need to try red, green, red, yellow. All these combination, you don't need to waste your time to test. In the backtracking can help you to reduce the number, but the number of possible case still in exponential times. You will find that, yeah. So if you try to use a recursive, you take the current index. If the current index equal to the number, then that is the answer. Else, you will try all the possible. You got m color, so you will try the first color, color 1, color 2, color 3, color 4 to color m. For each time you assign, and then you check every time you assign one color, you check this configuration is so-called safe or not safe. Maybe it's correct, it's valid or invalid. If it's valid, you carry on to choose the next vertex and then color it. Yeah, so you will keep. So this is that there's a for loop in the earlier slide. Is the for loop you will try every time you have so many possible case. So you will try which one is correct. And then if it's valid, then you move on. If it's valid, you move on. If it's you found that it's not safe, so-called not safe means that they are invalid, then you will stop and then backtrack. Then saying that not true, return false or failure, and then try another alternate one. Yeah. So then no true, there's been no more solution, then you only can, there's been this particular path is no solution. You have to backtrack. Yeah, then return false. Okay, so this is a very classic problem. Okay, this one you simply Google search, you should be able to find out. That's why I show you here. But what I think you to learn all these things is not simply Control-C, Control-V and run it. That's why take notes that assignment don't just simply copy your friend's answer. A lot of people do so. I already see a few people case doing that. To learn this, okay, you can find that that's what I highlight here. You can see that not surprising that there's a adjacent metric, adjacency metric to indicate about the graph. Then you can see that there's a for loop here. Then definitely there's a function to check is this configuration is valid or invalid. So they just every time you check whether this choice is valid or not. If it's valid, then you move on to the next vertex. So you will find that this for loop will keep trying different combination recursively. So this is a recursive function. And you run a recursive function in a for loop. Yeah. So the time complexity here, yeah, you can expect that is the m. That means you, in short, if I have how many vertex, if it's the number of, I just simply write now the recurrent equation. So this is the, let's say it's the number of function, the number of possible possible solution you need to try. So when you have this is the number of vertex. When you have this number of vertex, you will do something followed by, you will do some constant step. Maybe you need to run some let's say it's a constant or let's say I put it, let's say all this process I simplified to set is a constant time. So it's 1 plus, the key is this step. Because this is a for loop, you need to do m recursively, and then the problem size. After you color 1, that means that the number of uncolored vertex will reduce by 1. So you can imagine it's number of v minus 1. So roughly this is the time complexity. If you want to find the time complexity of this algorithm, which means that you need to solve this particular recurrent equation. When your W is left only when you reach 0, no more vertex, that means all are successfully colored. Then you just simply return true, maybe just a constant 1. Then you're trying to solve this equation. Not surprising that you got m iteration. The key is because you have m iteration to try all the possible solution. This one definitely is in exponential. Yeah, I think we will try. I think I will stop the lecture today. On Wednesday, I will talk about another one, which is the 8-queen problem or n-queen problem. Will be similar. Yeah, this one will have a similar problem as this coloring problem. The implementation also very similar. You will find that there's a for loop inside. Then you check whether this one is safe or not safe. Whether this arrangement, this configuration, you put the queen here, is it appropriate or not appropriate? Then you will try all the combination. Okay, before I end, quickly, get you some idea about the 8-queen before. I will talk about the details on Wednesday about this 8-queen problem. Same thing, 8-queen problem is trying to put 8-queen in this 8x8 chessboard. Then you need to ensure that no 2 queen can attack each other. The arrangement you put, so that's mean if you put the queen at this top corner, left corner, then you are not allowed to put any other queen along this and in the same row and same column and the diagonally, because queen can move. If those people knows how to play the chess, you know that you can move horizontally, vertically, and diagonally. So you cannot put the second queen in this location. So the thing is like you want to put 8 queen on the board. Same thing. This is the one of the solution. And no queen can attack each other. So the most naive exotic search is like just try out all the possible case. Put all 8 queens in the same row. No, not possible. Then you try another combination, another combination, another combination, another combination. Then there are 4.43 billion way for 8 queen only. Then a smarter one is if you know that each row only can put 1 queen, you can reduce to 8 factorial. Because each queen only can put in one of the location in each row. In each row, you only can put 1 queen. Either the first place, second or third or fourth or fifth or sixth or seventh or the 8th, the last position. So you got 8 factorial. Once you put it there, then only left 7 for the 7 possible position for the second queen. Then only left 6 possible solution for the third, and so on and so forth. So you try out all the possible 40,000. Not a lot. So is there any better way? Backtracking can give you a better solution. We will talk about it on Wednesday lecture. So today you learn about the backtracking. I just introduced the backtracking, which you learned from last week lecture, the depth search. And then you obviously can use this kind of a backtracking algorithm to solve some maze problem. I also introduced a very classic matte coloring problem. That one can solve. Then on Wednesday, I will talk about 8-queen problem. You find that you also can use it to solve this 8-queen problem. So the lesson you learn is not only can solve this 3 problem. You can use to solve a lot similar problem. Just like whether you can observe that you are trying to. You can find that those problems there are a lot of possible solutions. The thing I want to deliver here is that there are a lot of possible solutions. But at the moment, if you don't go and try evaluate each possible solution, you won't be able to know which one is the actual solution you want. So we need to try, and every time you try to add one more, you make one decision, one more decision, you will find out that whether this particular sequence, this particular path, is it correct solution or not. If it is not the correct solution, you need to reverse back. You need to backtrack one step earlier and then try another possible scenario, another possible option, another possible choice, and then move until you keep trying backtracking until you reach the actual the solution, the solution you want, the optimal solution or the best solution based on your problem. Then you can stop, and you are able to know that that is the solution. So every time you reach a leaf nodes, you're able to judge whether this is a solution or not a solution. There's a way for you to evaluate it. So you'll find that they always have a function. Whether later you will see the equine problem also have the similar things. They will check whether it's so-called is safe or not safe. Is it correct answer or not correct answer? So that you can carry on or stop here. No more solution for this particular combination, for this particular configuration. You need to try alternate one or not. Okay, so that is what you should learn in this lecture. Let me answer a few questions. If we have this one, I think I already answered. If you have two, I would say okay. The Hao Guang is asking is if we have two recursive call, the complexity is 2 power to n. So does that means that if we have 3 recursive call, the complexity? I will say first of all, if you have 2 recursive call, it may not be 2 power to n. It may not be 2 power to n. It's the example you see in the last week tutorial is 2 power to n, but it may not be. For example, you just simply change the last week tutorial question, which is each recursive call is n minus 1. Instead of n minus 1, every time you just n divide by 2. Then you'll find that the time complexity is no longer 2 power to n. The time complexity, if I'm not wrong, is in linear. So if you have 3 recursive, if 2 recursive call, if you do it on SAM, I think I can set yes. If the 2 is 2 power to n, because you can see that if you have 2 recursive call, you can draw out the diagram. When you do one function call, you will end up that expand it to 2 recursive call. Then 2 recursive call for further expand to another 2 recursive call. Then it's like in power of 2, power of 2, power of 2 grow. The number of recursive call is power of 2. If you have 3 recursive call, that means one function call, you will expand it to 3 recursive call. And then each of the recursive call will further expand another 3 recursive call, another 3 recursive call, another 3 recursive call in the same manner. Then if that one is 2 power to n, this one should be 3 power to n. For the code for current power, the m is the number of color. The m is the number of color. So I can choose m equal depend how many color I want. So if I allow 4 color, then the m will be equal to 4. At least you need 4 lah. For if you know the 4 color problem, yeah. If you can, yeah, I think less than 4. You may not always be able to, certain circumstances you may not be able to find the solution. There's no solution at all after you try out all the possible paths. I think m equal to 4 is for sure you can find a solution. So I just want to like I said, I check is the plagiarism. So if the system detect is a plagiarism, definitely they detect is a very like I said, to learn all these things is end up you just Control C, Control V. I have to give you 0 marks. Clearly that you learn nothing at all. To be fair to other students, you should receive 0. And the person, the so-called your co-pilot is your friends, then of course you should get 0 marks also. Your friends also should get 0 marks. Because he tried to let you learn nothing. So the penalty should be given to him as well. Okay. Any other question? If not, I will end the today lecture. So exercise, I think the first of all, I think the tutorial already give you a few. I think this week also have another few more questions ongoing. If you really want to try, actually a lot of quite simple, like just now I mentioned last week the tutorial question, I just simply n minus the two recursive call, instead of n minus 1, I just go and try n divide by 2, then I go and try to do it. Yeah, then that is another exercise question already. You can, like just now your friend asking the question, yeah, how about if I try three recursive call? You don't need to ask me whether it's 3 power to n. You can just try to try to derive the recurrent equation and solve it. Like what I expect is I draw the diagram, I already have I already have a good guess it should be 3 power to n. But how to verify it? Just trying to derive the mathematics equation is a 3 power to n. You do a n print in each recursive call plus 3w n minus 1. You just try to solve this equation, then you found whether is it 3 power to n or not. Yeah. So then you can, yeah, then that is another exercise. You can keep from one. Normally to learn the thing is not I give you 100 questions, you go and trying to learn that 100. It's like when you have one question, you have the question, okay, how about I do this, how about I do that? In programming, in mathematics, to learn it, I think that you will learn more to help you to have a deeper understanding what this particular problem trying to tell you. Yeah, when you try a little bit different, yeah, you try this combination, that combination, you modify a bit here and there, you're trying to solve it again. If you manage to solve it, that means you already understand the things. If you just do a little modification but you can't solve it, just simply imply that you still don't understand the things. So I think that will be good enough to practice. If you want, I think online you definitely can find a lot more. But I would say they're not very useful. It's like you just trying to memorize all the possible case in the end. When you find that you are just trying to memorize all the scenario, you not really understand the things. You just something like hard code memorize the things on it. It's not a good sign to you. Okay. Well, I know that if the system had detect plagiarism, no, you won't know. You only receive the result, you will know. We won't ask you, we won't tell you, then you go and modify until you won't get caught. You get caught means you get caught. Okay? If no other question, I will end the section. Thanks.